Hello, everybody. So a very quick intro about myself and my colleagues. My name is Alessandro Benedetti. I'm director at SEES, and I am the chair of the Apache Solr PMC member and committer of Apache Solr. Today I'm here with my Apache Solr hat, but I'm also director at SEES, an information retrieval consulting company. My colleague Ilaria, she's working as an information retrieval and machine learning engineer at SEES, and she's also a committer of Apache Solr. My colleague Anna, R&D information retrieval and machine learning engineer, and maybe she'll become committer one day. So very short intro about our company as well. SEES, we are headquartered in London. We are distributed as a company, and we are open source enthusiasts. So we work with open source software, and we contribute back to open source software, both in terms of code and support and talks at conferences. We, as a consulting company, we work with Apache Lucene and Solr mostly, but we had a lot of projects, and we have a lot of projects with Elasticsearch, OpenSearch, and a little bit of Vespa as well. We are community contributors, as I mentioned, and we explore the cutting edge of information retrieval and AI integration through active research and blogging and paper publication and contributions. Hot trends, so what we are working the most these days: large language model application to search problems, vector-based search, natural language processing as a whole problem in general, so many sub-problems in there, learning to rank, so the application of machine learning to improve the ranking of search results using additional information on top of the information the user information needs. Document similarity, so they're more like this. We've been working a lot on that. And search quality evaluation, so measuring the quality of your search engine is extremely important to understand how to improve it. A little bit of self-promotion. I wrote recently a book about large language models and search engines, mostly covering like open source search engines and how they interact with AI and large language models. Has been released in January, so if you're interested to read about how you can use large language models to improve your search engine, it can be a good read. So today we are going to talk about Apache Solr 10 and what's coming with 10.1 mostly. We put 10.x in here, but the next release is going to be that 10.1, so most of the features I'm going to present are going to be there in the next release after Solr 10. And this is going to be like a carousel of many features. So we are not going to be able to cover the internals and how each feature works, but I want to give you like an idea of how you can use it, what's like the scope of that feature, how it can be useful, and then you will have like the link to the Jira. You will have like the possibility of scanning a QR code, access the Jira, take a look at the pull request. We have a blog more or less for each of these features, so you can read about it in the blog. So if you wanna, dive deeper in each of those features, you will be able to do it offline. So the first two new features coming to Solr 10. Solr 10 has been released, so we're going to talk about features that are currently available with it in regards to vector search, relates to reducing the memory footprint of your search system and speeding up your query latency in the vector search domain. Specifically, we are talking about quantization. So probably many of you heard of quantization, and in Solr, we now support two types of quantization: scalar quantization and binary quantization. So first, let's talk about the scalar version of it. So the scalar quantization means we compress float 32 bits elements in your vector to 4 or 7 bits elements. This guarantees a reduction in memory, a speed up in latency, but as you can imagine, you are compromising on precision, so you're losing some information. But losing information can be acceptable for your use case, given you're going to get like a better memory usage and quicker queries. So this happens through a new schema field type, the scalar quantized dense vector field. So this is configurable in the schema. we're going to see how you can configure it in the schema. And it builds on top of a Lucene implementation. So the Lucene 99 HNSW scalar quantized vectors format, and with Solr 10.1 coming, there's a Lucene like upgrade that side with some minor changes and deprecated parameters I'm going to introduce. So if you access Solr 10, you are going to use this internal, but in case you go with 10.1 as soon as it's released, you're going to have like an upgraded internal Lucene codec. So we are not going to spend much time on the algorithm, but just to give you an idea what means like scalar quantization, it's very similar to min-max normalization effectively. So you take a look to all the elements values you have for each dimension in your vectors, and then you calculate based on some parameters if you want to consider all of them or keep out the outliers, because maybe you want to consider a smaller like dimension space to compress, and you fill a smaller amount of buckets. So you take like some of the values you have originally encoded as float 32 bits element into a smaller amount of buckets, potentially for an integer with 8 bits, but actually then it's represented internally with 7 bits or 4 bits. So you're losing some information, but you speed up the entire system, and also the memory footprint, you improve it effectively. Now, right now in Solr 10, you will find these 4 parameters. The most important and one parameter that is going to stay with 10.1 is the bits amount. So you decide how aggressively you want to compress your original float, 4 or 7 bits. And the rest are parameters that are in Solr 10, but they got automated in the following up Lucene codec. So in Solr 10.1, you don't need to configure these parameters. Just to give you an idea anyway of these parameters, they affect, as I said, like the amount of values you consider for the min-max normalization, pretty much. So potentially you want to keep out a certain percentage of outliers. So you calculate, for example, a parameter of 95 confidence interval. It means that you keep the central 95% of values from your vectors for each dimension, and you ignore the small outliers, 2.5% of small outliers and 2.5% of big outliers. So you keep like a central window of 95%. Dynamic confidence interval allow you to sort it out automatically, and decompression is a way to even more aggressively reduce the storage, spending a little bit more time decoding for 4 bits configuration. So all of these deprecated. So from 10.1, you don't need to configure them. This is an example of a Solr 10 schema with this new field type. So as you can see, it's actually quite simple. So you define the field type in the schema, and then you are going to use it for some of your fields. You specify the amount of bits, the confidence interval in this case, and compression to true. So we are literally adding just a couple of parameters in the schema to make the quantization work. The binary quantization is a similar algorithm effectively, to the extent that you want to use it again if you want to reduce the memory footprint of your vector search and speed it up more aggressively. So in here, we are encoding, compressing your original float 32 bits to 1 bit, so just a 1 or a 0 value. And this means that you are losing way more information, as you can imagine, but you are speeding it up a lot. So, as I said, link to the Jira issue, and we have a blog post. It's based on another Lucene contribution. And to give you an idea of how it works, it's based on actually like a combination of Lucene work and a couple of papers from different research groups, but the main idea is that you calculate a sort of centroid vector, the sort of, like we can imagine as a sort of central vector for your corpus of information, and then when you are compressing your vector to the binary version of it, you check each dimension value. If it's greater than the centroid, you go with a 1, or if it's smaller than equal, you go with a 0. Because we don't want to lose that much information, the algorithm implements actually in external data structures some corrective factors that are applied when we calculate the distance to avoid to lose too much in terms of information. It's an asymmetric algorithm, so you don't have to worry that much about it, but the query vector is actually encoded into a 4-bit representation for each element, and the storage, so what your corpus of information is going to be 1-bit vector in the index. At query time, you're not going to define like the distance because it's not configurable. So you don't specify like, I don't know, the cosine or the dot product because it's just happening through a very specific distance. That's the ideal one for this specific algorithm. When you should use it, when you're dealing with like huge data sets, you're not happy with the uncompressed query times and memory footprint, you are unhappy with scalar quantization, so you can go a little bit more aggressive and check both the throughput, of course, memory footprint, latency, and quality impact. As I said, this is an example of the schema, so you can configure it, and no need to specify the similarity function because that's coming with the algorithm itself. So a short recap about those first two contributions. Scalar quantization, you need to reduce your memory and query latency. You can tolerate a drop in accuracy. Of course, I always recommend to benchmark how much is it for your specific use case. Binary quantization, the scalar in memory reduction was not enough. You want to go even more aggressively, and you can tolerate a additional loss of information. So now I'll pass to Ilaria for the rest of the features.
Okay, yes. So let's move to another contribution. Now we talk about the early termination strategy, in particular the patient KNN vector query. To introduce this feature, let me first give you a very high-level overview of how HNSW graph search it's done. So generally, we start from a predefined entry point in the upper layer of the graph, and then you follow links towards nodes that are closer to the query, and then from there you move down layer by layer until you reach the bottom layer. The bottom layer of the graph is the one that contains all the nodes. So in this case, the search continues until no better nearest neighbors can be found compared to the one already identified. And so this phase can be very expensive, so especially when dealing with large data set. And many often the algorithms keeps continuing exploring many additional nodes, even if the results are already stable enough. So the main idea is, why continue exploring the graph if the results are already stable, so are not improving? So this is the intuition behind the patient in proximity research paper that was presented last year at HNSW, that inspired the Lucene contribution first, and then the Solr support. So it's one of the authors of the paper, Patient in Proximity, that implemented this feature in Lucene, and you can find it from the version 10.2.1. So in particular, two main components were added. So we have the HNSW Q saturation collector, which monitors how stable the nearest neighbor's Q is during the graph exploration. And then the patient KNN vector query, which is a new type of KNN vector query that use this collector in order to optimize the HNSW searches. So the mechanism is regulated by two different parameters that are the saturation threshold and the patience parameter. In this case, the vector query will exit early the navigation of the graph when the HNSW queue saturate over these saturation threshold parameters that measure how stable the nearest neighbor queue must be to count as saturated for more than patience time. So patience is the number of consecutive saturated steps before you exit the navigation of the graph. So it's the number of iteration you are willing to do before exit early the navigation. Implementation in Solr. So when the Lucene version of Solr, when in Solr the Lucene version was upgraded to 10.2.1, we were able to add the support for this feature that was implemented via the KNN query parser, and we basically added just 3 simple query parameters. So you can find the early termination parameter, which is used to enable or disable the feature. It's a Boolean and the default is false. And then we have the 2 parameters that regulates the mechanism. So the saturation threshold and the patience that I already explained earlier. So in this case, you can find the saturation threshold, that it's a double, and the default value is 0.995. So this means that the number of newly collected neighbors is less than 0.5% at each iteration. And the patient parameter is an integer. But as you can see, the default value, it's not a fixed value. It's a formula here. So it means that you take the 30% of the top k, but never less than 7. This is because if you use a value that is too low, maybe it could be too aggressive, so you exit the exploration of the graph too early. But in contrast, if you use a value that is too high, it can reduce the benefit of the early termination. That's why it is decided dynamically based on the top k that you specify. One thing that I want to mention is that these default values are not Solr specific default value, but these are the default implemented in Lucene. And if you are curious, in the PR, there is also in the comment they perform some benchmark in order to choose this value. So if you are curious about that, you can take a look. And also that saturation threshold and patience must always be used together. So if you want to use the default, you can omit both of them. But if you want to custom them, you have to pass them together. You cannot customize just one of them. Here, just some Solr query example. So in the first one, so yeah, we have the KNN vector query. So as you can see, we specify the KNN query parser, the field. In our case, is a dense vector field, top k, and then easily, if you want to enable the feature passing using the default value, you need just to pass the new parameter early termination equals true. In the second example, I just show you an example where you can pass the other 2 parameters and you can use a custom values. In this case, as you can see, there is no need to also pass the early termination parameters, because automatically when you use the other 2, it's automatically enabled. And in the third example, I just want to show you the same concept also apply to the text to vector query parser, which is a parser that you can use if you want to vectorize your textual query using a predefined language model directly and internally in Solr. So since the text to vector query parser extend the KNN query parser, it directly inherit the 3 new parameters and the feature. Just a recap, when to use this feature. For sure, when you have a latency sensitive search, so when times matters are more important than recall, and when you have many vectors that are very similar, to each other, so you have near duplicates, because in this case it's even more true that the queue of the nearest neighbors will become stable earlier, and so performing additional distance computation than necessary, it's not needed because you reach almost the same accuracy. Okay, now let's move to another contribution. Now we talk about the seeded KNN vector query. Here, the main idea is to use a seed query in order to reduce the candidate set before vector scoring. The Lucene implementation was based on the research paper Lexically Accelerated Dense Retrieval that was presented at SIGIR in 2023. And yes, the main idea of the paper is that you start from a fast lexical query in order to find a good promising set of candidates, and you use that one to start your navigation of the graph. So you can think this feature like an hybrid search, but yeah, it's not just mixing score like in the hybrid search when you receive the result from two different queries and you mix the score. But in this case, it's a computational pruning because you will perform less vector comparison because you will not explore the entire collection, but yes, you will just explore the semantic space around these seeds document, these seeds candidates. So Lucene implementation, again, you can find this feature in Lucene starting from version 10.2.1, the first PR, even if others PR followed because there were some bug fixes and also some refactorings. But yes, it was implemented via the Seeded KNN vector query, which is a wrapper around existing KNN queries, the KNN float and KNN byte. And as I said, yes, you just start from a lexical search first. You will receive your seed top docs, and then you will use this document as entry point for the HNSW graph traversal. And the support in Solr, it was implemented again via the KNN query parser. In this case, we added just one query parameters, the seed query, which is an optional, and you can specify any type of Lucene query that will be used to guide the vector search. Here again, some Solr query example. So in the first example, I just want to show you how to pass the new parameter, seed query. So here we have specified a query. So in this case, a document that will match ID 1, 4, and 10 will be used as entry point for our HNSW graph exploration. If no document match the seed query, it will fall back to the regular, let's say, KNN query. And then in the second example, I just want to show you that if you want to use both together, the seed query and the early termination strategy, you can do it. So you can pass both the parameters. And in this case, early termination strategy will be applied on top of the seed query. Again, a recap, when to use this feature. It will be useful for sure when you have a high quality lexical candidate set to start with. And also, yeah, as I said, it's a kind of hybrid search. So if you want to perform a vector similarity only on relevant documents, so for example, you want to combine exact terms, IDs, brands, product names with their semantic meanings. So this could be very useful. Now passing to Anna for the next part.
Thank you. So another news in Solr 10 is the introduction of this parameter that is called filtered search threshold. This is regulating when and how the Acorn-like implementation that is currently in Lucene is used from Solr. So Acorn is an algorithm, and here I put actually the link to the research paper if you want to go in depth, that change both the index graph construction and the query time navigation of the graph. But in Lucene only, the query time part has been integrated, so the HNSW graph construction is the same as usual. And the main idea is that when you have some filters, and mostly some very restrictive filters that are removing most of the documents you have in your collection, you can use a different approach to navigate the graph to get better results. So the idea is that you still evaluate each node, and before scoring them, you are like checking if they meet or not the filter condition you have. And since the filter is very restrictive, probably you will skip most of the nodes. So the idea is also to inspect the two hope neighbors of those nodes to be able to still get those part of the graph that will be disconnected otherwise, and that potentially could contain some relevant nodes for your search. So the main idea of this algorithm is to check filters during query search before scoring nodes, and also exploring additional nodes with this two-hop exploration. And specifically, the parameter is like the one deciding if we are going to use this approach or not during the KNN search. So in Lucene, this is implemented through the filtered HNSW graph searcher, and it is also integrated into the KNN search strategy. The parameter is could be between 0 and 100 as a value, since it is like a percentage, and control the filter traversal. So 0 means that we are never going to do ACOR-like navigation, while 100 is always use it. But actually, what it has been seen through some benchmarking in Lucene is that it is not always worth to do this kind of additional checking of nodes. And so the value that actually comes from a benchmark is that if the number of documents that match the condition after filtering is below the 60%, then we should go with ACOR-like navigation. Otherwise, we should go with the classical, let's say, HNSW traversal at query time. So Solr exposes this parameter through the KNN Q parser. So here is an example of how to use it. So in this case, I just put the default value, but you can customize it and put everything you want from 0 to 100. So you define the KNN Q parser, and then apart from the field and then top K, you can add also this parameter once you have a filtered query. Our recommendation anyway is to always benchmarking. So before deciding the value of the threshold, try some of them, verify if the results are what you expect, both in terms of quality and timing, performances, and see which could be the right one to choose. So when to use it? As I said, this is very useful mostly for very restrictive filters, since otherwise we could find up in skipping most of the nodes. And with this kind of navigation, we actually achieve a better recall and also a potentially large speed ups, since with ACOR we are not scoring those nodes that do not meet our filter. Otherwise, we will do anyway. So this is the speed up part, but it is worth it only if we actually have a very restrictive filter. Otherwise, in the worst, let's say, scenario with a broad filter, the last one, we will do this additional two hope neighbors exploration. We are then scoring those nodes, but it wouldn't be necessary, since anyway the graph will be connected. We will accept most of the nodes, so probably the classic HNSW will be fine anyway in this case. Then another one is the EF search scale factor. So here the problem we would like to solve was that there wasn't a direct way to improve the recall for vector search, apart from increasing the top K value. But top K is just telling us how many results we will have with vector search and not the quality of the results we have. So the idea here is to actually expand the nodes we are considering during the search to be able to get the most relevant one. So increase the probability to get the best nodes during the search exploration. How to do this? So the name is EF search scale factor, since it impacts the EF search parameter of the query navigation of the HNSW graph. So instead of directly defining this parameter, we compute it, multiplying this factor for our top K. So the default value is 1. This means that we just collect top K number of candidates during the search, and then from those top K, extract the one to return to the user. But thanks to the EF search scale factor, we can actually set this in a greater value than 1. So telling Solr that we would like to explore more candidates, and then from these more candidates takes the top K1 we would like to return to the user. You can also do the opposite if you want actually to speed up the search, but keep in mind that you probably will end up with a lower recall. So again, benchmarking, testing, and see. And this parameter is supported for both byte and float vectors through the Solr KNN vector query and the Solr KNN float vector query. And again, the example, very, very simple as the other parameter we have seen so far, just put in the KNN query parser. So first wrap up of everything we have seen so far. So the first part at the top is related to the memory and latency saving. So for the indexing part of the KNN search, so talking about the quantization. So if you need a memory and latency saving with a small recap drop, you should go with scalar quantization. If you actually need more saving, so a great a great memory saving with a great recall drop, go with the binary quantization. Then at the bottom we have the query time, let's say, part, where if you have some good lexical signals, you can explore the Seeded KNN to be able to exploit also those good results. Then if you care about latency and also you have a collection with near duplicates document, go with and try with the early termination. Otherwise, if you care a lot about recall and less about latency, you can explore the EF search scale factor, which allows you to get better result at query time without touching the index construction. And finally, for filtering, have a look at the Accord-like implementation. Just be very, very quick, a couple of mentions for just some renaming in some Solr modules for the part of the large language models and vector search. And then a couple of new integration that allows you from SolarJ to directly index vectors with primitive types, float and double, and a fix that has been done for the text-to-vector update processor specifically for partial updates.
Okay, so now I'm going to talk about what's coming next. So for 10.1 specifically, so all these contributions have been contributed already, so they are in the main Solr code base and they are coming with the next release. So the first one is KNN search on nested vectors via block join. So this is the possibility of performing KNN search on child documents. For example, like the classic case is when you have like a parent text with chunks, so a parent document with nested chunks, and returning the ranked parent document, so the original document. So is the classic multi-vector kind of scenario. And this is implemented in the KNN query parser through a couple of parameters, the parents, prefilter, and children of parameter. And this was already possible in Solr before, so like in Solr 10, but with this contribution, we are using a Lucene internal that guarantee the amount of parents you retrieve. So this means that you are going to retrieve top K parents. So you are collecting the children and you are keeping for each parent the best child. So this is possible through the diversified KNN query. and there are various parameters. So KNN to start, to kick off the query, and parents pre-filter in case we wanna filter the parents. So you're not gonna want to return all the parents, but only the ones satisfying a filter. And the children of is just a parameter that will get the all the parents as an input. So what happens is that you effectively are navigating the graph, so you are navigating the children, and then you are collecting for each child the parent, and whenever a new child is found that is better, you are updating the score effectively of the parent in the queue. So this is the syntax for the query, so it's a little bit intimidating. You don't need to learn it right now. Slides are going to be published, so you can find how you can do it. But just to give you like an intuition, you are going to be able to filter both the children, so metadata on the children and on the parent. So this gives you like plenty of flexibility. Through that implementation, we were able to contribute multi-valued vectors. So what happens is that if you have like a vector value with multiple possibilities, you are going to be able to do it in Solr. Behind the scenes, you are using this Lucene implementation. So what happens behind the scenes is that you actually use nested vectors. But this open up the possibility of having like multiple vectors in an original document and return those vectors, return potentially the best child per document, all children, so all the vectors. There are plenty of possibilities here. The syntax in here is a little bit simpler. At indexing time, you just push an array of arrays, and then at query time, you're going to use the same query time syntax we've seen with the KNN and nested vector search. An additional contribution is the addition support for like Colbert kind of calculation in Solr. So the possibility of having like multiple vectors per document to calculate like the maxim metric and use like Colbert models. So for these contributions that were developed by my team, I wanna thanks to anonymous sponsors, so I cannot mention the names, but this was possible through these donations, so I'm very grateful for that. So we were able to work on this thanks to those two organizations, so I much appreciate that. And I want to, of course, thanks also the work of Anna and Ilaria that helped with these contributions. So thank you very much, guys, and we should have like a little bit of time for questions.
Thank you very much. Yes, there's about 2 minutes left for Q&A. Are there any questions in the audience? There's one. All right, I'll come to you with the microphone.
I can use these features when I'm using Lucene directly. These are all implemented in Lucene?
Yes. So all of these features are implemented in Lucene and exposed in Solr. So in case you are a Lucene user, you can leverage all of them, possibly a little bit some more upgraded version, because it takes a little bit, since the split with Lucene and Solr, it takes a little bit more time to bring them to Solr, but they are all in the original Lucene.
Any more questions? Yes.
I have a question regarding the Econ approach. Do you have any experience on the fraction of documents that should be filtered that it might be sensible to use this approach? So like 80% filters, 90% filtered? There's a value like 60% here, but I'm not sure if it's like just a parameter for the approach or it's like an overall good value.
Do you want to answer? I can answer. So we linked here also some Lucene benchmarks. So when they did these benchmarks on a, of course, like data set, they experimented that 60 was like the nice trade-off in terms of like the additional computations, but the the advantages, the benefits of like the selective filter. So that's the reason that the recommended threshold is 60. So I don't remember if it was just one data set with some benchmarking on it or multiple ones, they ended up with that magic number to be decently good. So I think probably it's a good starting point. I would, to be honest, I mean, we didn't have right now the possibility of using it with some customer, but if I was to use it in a production system, we first benchmark on the data set of the customer, starting from 60 because there's already some studies behind, but I wouldn't just go there with 60 and go to production immediately.
All right. Unfortunately, time's up, but I'm sure our speakers will be available at the conference all 2 days. So find them, hit them up with their questions. And again, give it up for our speakers.